Quintero. I am the research scientist here at FIU. This Tech Talk series is focused on D&D topics relevant to the DOE EM complex. This event is sponsored by the U.S. Department of Energy and Environmental Management. Please allow me to introduce our speaker. Today, we are joined by Alejandro De La Noval. Alejandro is a graduate from FIU with his master's in computer science in 2024, where he applied his AI ML towards groundwater modeling and contaminant forecasting as a DOE fellow. Currently, Alejandro works at the Savannah River National Lab, where he entered as part of the DOE Fellows program, using natural language processing and large language model orchestration in projects that help automate knowledge transfer, groundwater analytics, and site loan monitoring deployment. So without further ado, let me welcome Mr. Noval to this presentation.
Thank you, Walter. Welcome, everybody. Today I'll be presenting AI Asset, AI Accelerated Strategy Solutions in Environmental Technology. Just a quick note, this presentation was presented this year in Waste Management 2025. So if you were there, this will be the same slides. But without further ado, I'll go ahead and start. So AI Asset works off of what Altimus is in the present day. You in this meeting might already know what Altimus is, but just a quick recap. Altimus is an integrated network of different sensing technologies to monitor a complex hydrochemical system, like those groundwater systems at our national sites, the SRSF area site being one of them. But the key concept of Altimus is to utilize proxy variables to measure in the sensors that we're measuring to predict plume anomalies. Proxy variables may be stuff like pH, specific conductance to predict particular anomalous analyte. The idea being that by controlling these proxy variables, we don't need to put in as many wells, nor do we need to sample wells as often, resulting in a potential 80% reduction in wells, and that's $12,000 to $20,000 per year per well saved, and that's because of that reduced sampling frequency. So you can see here on the right that the your typical long-term monitoring system under Altimus has its well sensors, temperature sensor networks, is wetland and air monitoring stations, and that goes into your modeling, which goes into your ML AI, which is that information is then used to further educate how we will continue our prolonged monitoring. So, but how did we get here? Well, Altimus started at the SRS site, and the SRS site is a site with a complex history. There has been historical cleanup efforts implemented over the years. You can see the timeline here. There was waste discharged into the basins. Those basins were capped and closed. Then there was pump and treat. And from 2003 to the present day, we have a funnel and gate base injection. And each one of these kind of points in the timeline kind of highlight a zone of vulnerability, right? These are places where if destabilization of the otherwise stable waste were to occur, those would be the first places of a plume expansion. So it's the contextualizations of these zones of vulnerability, these points where the system might fail, that is really important for us to understand and contextualize in our data. So looking at 2014, kind of an early look at Altimus as a concept, it started with 3 researchers. They were doing what is now considered pretty preliminary analysis, just kind of doing your standard correlations between your analytes and your your specific physical water properties, like specific conductance with nitrate, specific pH with uranium. And they did this for every kind of combination that was relevant. And it was a pretty long and tedious process to kind of analyze each one of these combinations. And but it was enough at that point to kind of propose an initial pilot scale sensor study with 3 wells. As you can see here, we have the gate and the base injection, and that's kind of the beginnings of the systems. You can see here spikes that correlate together with the injections of at the base, and this is what I was kind of mentioning before, where the contextualization of these zones of vulnerabilities is important, because when you take a time series models like this and you feed it into a time series model or regression model, you're kind of leaving the model to figure those spikes out on their own. But if we contextualize and give reasons for those spikes, like yes, these spikes are there because there was a base injection at this time point, then it offers guidance to the model. So this is what we mean by contextualizing those zones of vulnerability and why something like that is important. In 2015 to 2020, there was also a comprehensive simulative groundwater model application to kind of mess around with the environment, see how a plume would continue in time if you were to change rainfall, the layers in the subsurface and so forth, porosity, things of that nature. This is a simulative model, not a AI model per se. It's a separate model. And then we have our actual AI or machine learning models that kind of at this point in time have automated a lot of that exploratory data analysis back in those comparing of correlations of specific conductance and X analyte that we saw back in 2014. We've automated that. We've quantified those correlations. We have some common filter estimations, and we have some sensor network optimizations where we interpolate the different analyte samples at different well points, and we try to sub-select the amount of wells that still give the same efficiency in monitoring without upkeeping the extra cost for the extra sampling and extra wells required at the current day. And then there's kind of everything in between. There's additional geophysical characterization in the organic layers. There's the highlight of radiation hot spots, kind of additional characterization of the wetlands and SRS with apparent conductivity, just kind of extra information gaps, extra efforts that were used to cover things that weren't able to be covered with your simulative modeling and a traditional AI modeling. So all that is just to say that by AI Altimus is a big effort. It's a big project, and by this point in time, we can start to extract and generalize a workflow that we can apply to other sites. All that you have seen in the previous slides were applied to the SRSF area, but there are other sites looking for a long-term monitoring, a long-term monitoring solution to apply. And what's this generalized workflow? We're talking about knowing the site history, identifying those zones of vulnerabilities, analyzing that historical data, filling out those knowledge gaps, choosing the correct sensor technologies. In the case of Moab, another national site, that site has a lot of ammonia in its groundwater, which SRS doesn't have. So there are specific sensors that measure ammonia in situ that wouldn't very make sense to have an SRS. So choosing the correct technology to continue your monitoring, taking into consideration those regulatory considerations in that area, what is the goal, what is the standard they're trying to keep, what is the contamination they're trying to bring down, selecting the appropriate ML methods for those sensors, for those regulatory considerations, and implementing them. So then that's where AI asset comes in, right? We want to introduce AI asset as a tool for knowledge management and knowledge transfer onto other sites. And the idea is that AI asset would help in kind of transferring and applying that workflow to another site or separate workflows within SRS if not already established within. And here's AI asset as a conceptual system design. So essentially, it's has a reasoning agent or basically an LLM in the backend, kind of acting as your reasoning agent, as your workflow for selecting and automating a lot of workflows that are otherwise hard to program logically. So how does that work? Well, we have a database, which is a knowledge graph that is formulated by the ingestion of different data sources. These data sources can be anything from PDFs, videos, audio files, images. They're all ingested into the knowledge graph as nodes. And those nodes are going to be separated into a lexical and a domain layer. And we'll go more about how that knowledge graph is constructed in the later slides. But the idea is that once those nodes and connections between those nodes are established as a knowledge graph in our graph database, we can give the system a query, the query that shows a need for knowledge. That query will be vectorized and compared against all the nodes in our knowledge graph, such that the relevant and appropriate nodes to our query are pulled along with the query itself and fed into our knowledge processing module here, where we take that context that we've grabbed from the knowledge graph together with the query of it itself to decide on a workflow, one or multiple, to deliver a target deliverable. So this is how that knowledge graph is constructed, how that knowledge graph aids in delivering that target deliverable. And here you can see the domain and lexical layer I alluded to just now. The lexical layer is what I think industry and most people know as your RAG approach to augmenting your prompts, retrieval augmented generation. So basically, in terms of how this is represented as nodes, the documents are chunked out into different chunks and then connected, as you see here in the abstract visualization on the right-hand side. And then every image is also chunked out, every table would also be chunked out, and all of those will be part of a document or connected in one way or another, right? Those relevant chunks are what's pulled out when you do a similarity search against our database together with a query to give you an answer. But what makes this the reason for being a graph database as opposed to a regular database is that each one of those chunks have what's called a domain layer, right? Each one of those chunks have text or images or whatever. For the most part, at the current stage right now, it's all just text from PDF files. But all the chunks of text have their entities extracted as nodes and has the relationships between those nodes in that text extracted as well. So an abstract extraction of a chunk would look something like this. If you have a piece of a paper talking about a contaminant and how it moves, this is how the domain layer for that chunk might look. It might illustrate contaminant. It's in a medium, a layer of the subsurface. It's moving from a point source from a factory waste, or it was at one point a coolant for the nuclear facilities or whatever it is. It moves by a transport process, it converts into something else, etc. Right? It goes into a point of discharge. So that is the kind of the goal, kind of schema we want to extract from each one of our chunks. One chunk might contribute to part of this schema, but the idea is that all the chunks, because they'll all extract into the same entity node, and they'll all extract into the same relation between nodes, that this domain layer across all the chunks will start to be built out. So then this is kind of more familiar. That's how our database is constructed. How we take those entities and the context from the domain layer and the context from the lexical layer is very similar to how you do it in regular RAG, right? We have our raw text, which is augmenting the query we give into our prompt. And what makes this a graph RAG approach as to regular RAG is that we're also providing the relationships that we have just illustrated in our domain layer as augments to our prompt as well. So contaminant uranium node or uranium contaminant node is determined by the tailings product node, et cetera, as you see on your screen. It aims to deliver the intent of the text without the extra verbosity, giving the LLM or the reasoning agent more concise context. And again, this should be familiar, just your standard like prompt, especially nowadays with the rise of LLMs. You have our query responding prompt and our domain layer graph expansion prompt, and I'll go more onto the domain layer in a second. But the right side is kind of how your generalized prompt for standard QA. You define your guidelines to answer the user's query. You provide the context, you provide any tables, images as additional augmentation, and you also provide that those entity relationships within as well within the prompt to get your final answer. That is how the general Q&A happens when you have your system ready to answer queries. But as you're building out that database, it is very tedious. Imagine yourself going through all the different chunks in your text and having to identify nodes and classify organizations and pull that out and put that into a database. So to do that for the worldwide corpus of text, it's very tedious. We need to automate that, and that is also automated using LLM. We ask the LLM, given a chunk of text, to extract all those entities, those relationships in a structured JSON format so that we can automatically put that into our database. And this is how, well, this is the result of that domain layer expansions. You can see here, this knowledge graph is just a bird's eye view used in our Neo4j database. It was built using 150 documents from environmental reports, technology roadmap, scientific publications, etc. And you can see here all the nodes and how they're connected, all the kind of entity categorizations those nodes fall under, and you kind of want to see these clusters of nodes, because clusters of nodes means they're all nodes that are relating to each other, and those nodes that are clustered together are more able to answer a particular type of question. Right, so you want to have, ideally the graph would be all interconnected, and that's really going to give you that cross-sprawling relational context. But in reality, what you see is different chunks of your clusters of entities are more suited for a particular question. So this is a example QA response, describes oil and groundwater characteristics at the Moab site. We fed it with relevant documents, and this is the answer that came out of that. This was using, at this point, I believe, because we've jumped through a couple models, language models, but this one was given with Llama 3.1, the 8 billion parameter 4-bit quantized version. But that's kind of your standard LLM fare. What's really kind of the point of AI asset, because you can only get so far with your QA, and QA is a part of AI asset. I'm sorry. Okay, seems like someone unmuted by accident. QA is a part of AI asset. But what we're illustrating here on this slide is a automated set of prompts that more realistically get you to your goal. So if your goal is to design and implement a long-term groundwater monitoring system at Moab, one prompt isn't going to realistically give you that answer. You need to set up a workflow, a series of prompts and logic and external tools that are programmed logically without the use of AI to help deliver that final answer, that final product. But how do we give that the user, how does the user know which chain of prompts, which chain of queries to wrap, which tools to call upon to execute on that deliverable? So we want to kind of have different sets of workflows, different sets of prompts that we illustrate via some sort of UI, multiple choice interface. At this point, it's been kind of full thought down to a form selection where you choose kind of in a multiple choice fashion what you want to do, and there's going to be a machine generated prompt that is prompted in just the correct way to get to your answer, so that you don't put that onus on the user to create a thoughtful prompt. So we have that capability, that workflow selection available. We have that QA, your standard QA response. We also have image capabilities of now multi-modal models. And an example of that is this figure on the right here. We have a figure of the Moab site. And as an example, we asked AI asset, what is the distance between the center of the salines pile and the closest point in the Colorado River? And if you, with your eyes, take this scale in feet and kind of measure out the distance, that distance is approximately 1,750 feet, which is what AI asset gave in response. So there's your image answering capability. We also have this other capability that LLM has the ability to, which is call upon tools. Like I said, it's not just answering your queries in standard text, but it's also executing on tools, on functions, on programs that already exist, right? And an example of that would be like asking the coordinates of the Moab site. And this is kind of put here to illustrate areas of improvement. We asked the coordinates of the Moab site, and it gave us coordinates on the left here that are in proximity of the Moab site, but the actual Moab site is what you see here on the right. So this is kind of an indicator of accuracy when it comes to a numerical response, like coordinates of a particular location. And there are ways to improve that, but those improvements come from how we built out our database. The database is made with a bunch of documents, is going to do as well as what those documents contain. But if we embed GIS graphical layers in that knowledge base, you can expect a higher accuracy response to this tool. And the tool that we're calling is that visualizer you see on the bottom here. Now this tool isn't actually implemented, but it's there as to illustrate that ability. The tools that are implemented are tools as you see here. These are example tools currently implemented in AI Asset, where if you say provide a plot of the elevation near the F area basins, it'll call on the already logically programmed Python functions that generate these visualizations you see here. And it's important to note as these visualizations are not generated, they are produced by logic kind of hard-coded quote unquote code, right? There is no AI making these images. So you can be sure of its accuracy because it's traceable more so than an image generated from a model. More impressive is the prompt you see on the right, where we asked it to provide concentration profiles of iodine at the F area. So you can see here that AI asset is able to identify the area, it's able to identify the analyte, and it's able to identify the range we want to illustrate. And these are arguments to your function or your tool or your program that the LLM is calling correctly to produce the result you need to answer your query. And you can now start to imagine a bunch of these different tools called at different point on your workflows, orchestrated in such a way such that you can get your final target deliverable. And that's what AI Asset intends to do with the objective of that knowledge transfer, that knowledge management, particularly taking what we've learned at Altimus at the SRSF area and transferring it to other sites like Moab, which is used as a vehicle for demonstration in this presentation. So these are kind of the conclusions and next steps and kind of where we're at right now. We want to, AI Asset as a whole intends to reduce that technology transfer time by leveraging these principles of knowledge management and more importantly, contextualizing this information. We want to automate those generalizable workflows. These are spatial, temporal analysis, those correlations, visualizations, that model training where you don't need to know how to code or build a model, but you can just ask the LLM to do it for you. Particularly call on the tools that already exist, tools that may exist in Pylon, for instance, which is a software package available under the Altimus umbrella. And our next steps are to enhance that knowledge integration. So adding things like GIS layers to our database and tying it together such that we have a more fruitful context at retrieval and continue to build out that suite of tools and integrate them into the workflow so that we can get a more able system here. So that ends the presentation. I do have that was all conceptual, but I do have a kind of a little demo video. I wanted it to be live, but unfortunately, I was working on it this morning and it kind of bugged out on me, but I got a video on it. So I'll show you kind of what we have right now after waste management. The presentation on waste management is kind of when we started to build out this UI here, and it's kind of what you expect from the presentation, but just as a way to kind of see it in action. So here we're asking it, how does ammonia look at SRS? Said that doesn't have any ammonia data at SRS, which is true. SRS doesn't have ammonia, and I think relaying that information to the user is an important part of AI Asset. And the idea is that this interaction you see here, that in itself would be automated to some degree. So we ask it, then it's asking for clarification. We're saying just give me a highlight of the most significant wells, asking for further user clarification. And then we see here that visualization you see on your screen of ammonia at Moab and those appropriate selected wells. I want to look at a particular set of wells. So now we're scoping in, right? So we scope in, and this is verified. That's just how the data is and scaled. I want to compare two particular wells directly for higher quality comparison. Generates this plot. This plot is kind of expanded. Let's scale it down. And then you can see here kind of the final output, right? So this is kind of a video showing the idea of AI asset and work. And all these things you can see logically, they're just arguments to your Python function, right? So thinking about it from a technical point, you can see how something like this is created, right? So yeah, that's the end there. And there's also an ability to attach, copy, paste images, all that light and dark mode, all that good quality of life stuff. So that's kind of all I have to show for this presentation. I don't know if I went over or I went under, but feel free to ask any questions if you have any.
Thank you, Alejandro. That's a cool presentation, man. I like that interaction with the model you created. Let me open it to the floor. Anybody has a question for Alejandro?
Hey, Walter. This is Himanshu. Thanks, Alejandro, for a great presentation. It was really good. My question is, what's the framework you're using for knowledge graph here?
So the knowledge graph is hosted on Neo4j. There, for framework, there's not a. Are you asking like framework for how the knowledge graph is built, or just kind of how the database is deployed?
Knowledge graph is built actually, and of course the database as well, both basically.
Okay. So yeah, the database the graph itself is deployed using Neo4j. As for the building, that is a separate kind of coded out workflow. There's inspiration from, if you look up LLM knowledge graph builder by Neo4j, they have a GitHub. Pretty much what they do, how that GitHub builds out the entity of representation in our knowledge graph is similar to how we do it too. There are some modifications on our end, but that GitHub was kind of the inspiration of building out that knowledge graph. That, in terms of frameworks, like proper frameworks, because I wouldn't call that a framework. There is like the LLM prompting and all that, and under the hood is using LangChain. So I don't know if that answers your framework question.
Oh yeah, so it's using LangChain. Okay.
Yeah.
One follow-up question here. So you are using a chat, and this is based on the knowledge graph. Did you see how this compares with the LLM RAG approach here to get the similar response?
So there are moments where it depends on what's in the context, where like if a piece of information is in the node representations as opposed to the context. I will admit that a lot of time, whether or not you include that relational information doesn't have much weight on the final output, because most of if you're getting the entities from the text from your RAG context, let's say, it's gonna make sense that RAG, that information in those nodes are already in that context, so you can do without that textual representation. But because we query the graph from those nodes, and then from those nodes pull the relating text, we do find a more relevant retrieval of text. The prompt itself, when you include that relational, like node is related to this node by X, right? That stuff doesn't have much merit, but the relevance of the information is, at least to the naked eye, a little better, but that hasn't been like metrified or evaluated in any way with metrics.
Perfect. So, I mean, this is great work. So, are you planning to publish this in some journal?
So not in some journal. I do have this published in the conference for Altimus. I do eventually want to get there. I'm not happy with the project just yet. There's still a couple things I want to do. I want to kind of mature it a little bit before I publish it to a journal, but that is in the works, or at least I intend to.
All right. Thank you, Alejandro. What?
Any other questions from the attendees this afternoon? So, Alejandro, I have a question. Before you started working on this, I noticed that you had kind of the dialogue. You called it a multiple choice selection, how to arrive to a question prompt.
Right.
Was that? Yeah. Go back to that slide. Yeah. That is pretty neat. So basically, you kind of funnel through this dialogue to get to the question you want to arrive. Was that tell me about how you came up with that workflow? Because it's very interesting. I think I like that, how instead of coming up with your own prompt, you kind of like walk the user through a basically a funnel to get to the right prompt that they need to ask.
Right. I mean, this was together with Tom Dennison, my mentor here at SRNL. So we kind of thought of that together, but it kind of came up because, like, if you were to ask, I mean, it do a pretty good job if you go to the commercial LLMs even, and even the answers we get now compared to where they were like a year ago, like even in that like amount of time, the answers have improved dramatically with the deep research function that OpenAI has added to their models, and their image capabilities and all that. So now it has improved, but even despite those like improvements in that deep research, that web retrieval that they have, that Google also has. Now when you search on Google, it pops up. It's not like the answer is limited to text. Like you just get, you don't get that plan highlighted to you. It shows you how to make a plan. It shows you kind of guidelines on how to go about that, but it doesn't give you the plan itself. Which makes sense. When something is as complex like that, you need to break it down, right? So the idea is like, okay, we're not going to get there in an automated way with one prompt, so we need to break this down. But how exactly we break it down, and what way we break it down, and how do we ask those individual components, it's a lot of onus to put on the user. I mean, you just saw in the demo how much clarification I needed to ask to get, as impressive as at least I think it is, right, that it can do this. We had to ask a lot of clarification, like that wasn't all from one prompt, right? So that's where the idea of kind of putting all this in a UI format came from. Not to say that at least me as kind of the main technical person working on this project, I like to think I'm taking a text first approach, in the sense of like, I'm assuming I don't have any user help, but I need to have the functionality that takes in that user feedback, regardless, even if that's how I develop, because you can only get so far with that, right? So how that would appear in like something like this at this stage, Again, this is like a work in progress. I would have showed you the live thing, but something broke when I was working on it this morning. I'm thinking like these are all like functions, and then there's arguments to that functions. We can reduce the onus on like asking for clarification if like you ask it something and the LLM decides these are the applicable functions that I have, and then it pops up like a little form. It's like, this is what you need. Which one do you want to do? You click on that and then you provide the arguments kind of yourself, right?
Yeah.
And that might streamline a couple things, might ease the confusion that you might get in your standard like tool enhanced chatbot conversation like this.
No, I think it's pretty neat. I think it's useful even for like a new domain user, right? That might not have all the right, like you call it, parameters to put in, right? So it walks you through it and it gives you more idea. Okay, this is what I'm looking for.
Right.
Pretty cool. And the graph generation in real time is awesome. So that's great. Any other questions from the attendees this afternoon? Okay, so let me let's thank Alejandro for this great presentation. Alejandro, again, is a colleague. We work together on many projects here at FIU, and great to see that he's extending his expertise and SRNL. So congratulations, Alejandro. Thank you everyone for attending this Tech Talk. Please visit dndkmit.org/Tech Talk. I put a link in the chat to look at the previous Tech Talks. The recording for this Tech Talk will be posted on the website as well. Also, take a moment to fill the feedback form, which is also posted on the chat. It gives you some insight of the future topics you're interested in. So we look for speakers in that area. Save the date for the next Tech Talk. It's going to be October 21st, and the topic and the speaker will be announced as soon as we get confirmations. And finally, let me thank our sponsors, the Department of Energy Environmental Management, for supporting this effort. Again, thank you all for attending.